All right, guys, thanks for joining me again on another fun day of pre-calculus. Section 3.4 is what we're going to start with today, and that is titled the composition of functions. And that fancy word composition you may have heard of before, typically when dealing with music, and when it's composed of more than just one instrument. Well, now we're going to be composed or made up of more than one function. And we're actually going to have one function inside of another. Now they use this weird little O shape that kind of looks like multiplication, just like this kind of looks like, hey, we're actually multiplying those. We are not. All right. A composite function is when we have f of something. And what's inside of that thing is not just the generic, I don't know, variable x. It is now an entire other function inside of another. So that's what we mean by a composition. One function composed of or made up of another. Okay? Again, make sure that you realize the difference between a composition and multiplication. They will tell you take that whole function, f of x, and if they don't write anything in between, that means multiply g of x. But it does not mean when they write f of g of x. Those are not the same. Okay? So, as I put on here, these operations can be done in several different ways, and we'll see a few as we progress through. All right? With these algebraic functions. Algebra because there's letters involved. All right? Put a few key things on here I want to make sure that you make note of. That little weird symbol, that O looking thing, again, is not the multiplication symbol. Okay, I don't like it. So I would rather you guys get rid of that fog and just rewrite it in its equivalent form. Get rid of that weird little O and rewrite it as this, because that tells me exactly what I should be working with, where this doesn't so much. So if you ever see it this way, rewrite it in its equivalent form. Okay? So that's what I put for the second note. Other than that, let's make sure that we can work with it. Let's do a quick example where I give you one function I'm going to call f of x, and another function I will use the next letter in the alphabet after f, that's g of x. Notice they are two different functions. One is linear, one is quadratic. And I want you to find this first. Now, how do we say that? F of something, right? And I already told you what f of something is. F of something is 2 times that thing squared plus 1. So I already know, according to this, I'm going to have to write f of something, which is 2 times something squared plus 1. Now I can tell you just plug in some number like 2 in here, and you would do just that. A -5, you would do just that. And you do your order of operations, where it's parentheses, exponents, multiply, divide, add, subtract. In that order, simplify, give me the result, the output, the range. But they're going to tell us to put in an entire another function. So I'm going to use g of 2 in a different color. So what would be really nice to know? If they're asking me to evaluate f of that. It'd be nice to know what g of 2 is. Now, again, I know what g of something is, right? G of something is equal to 3 times that thing minus 5. Just like we knew f of something was equal to 2 times that thing squared plus 1. So I'm going to go over here and I'm actually going to plug in, just like we talked about, 3 times something minus 5. What did they want us to plug into that function? They wanted us to plug in to the g function a 2. And then when we find that value, they want us to plug it into the f function. So just like when we have multiple sets of parentheses or brackets in those order of operation PIMDOS problems, we're going to start with the innermost set of parentheses and work our way out. So there's nothing to do with the 2. So we go to the next set of parentheses and we're going to do g of 2. So I'm going to go over here and I'm going to plug in everywhere there was an x, a 2. And I will find that g of 2 is equal to order of operations, 3 times 2 first, which is 6, minus 5, which is 1. So now I know what g of 2 is equivalent to. It's equal to a 1. Which means now I can come over here to my f function again, which it said to do f of something. And we knew that was equivalent to 2 times that thing squared plus 1. And what did we just find g of 2 is equivalent to be? That value is a 1. So we can replace g of 2 with what we know it's equivalent to, which is a 1. Again, everywhere we had that x, that parenthesis, that's what we're going to replace it with. So in reality, the f of g of 2 is asking us to find f of 1. So if you just break it down into smaller chunks, starting on the inside and working your way out, now you know you're actually just finding f of 1. And you know order of operations, exponents first, because there's nothing to do with that 1 in the parentheses. Square 1, you get 1. Multiply by 2, you get 2. And then add that 1 and you get 3. So we know f of g of 2 is equivalent to 3. That's it. It's that simple. Don't get bogged down by these weird formats and multiple things being input. Just start with the innermost and work your way out. Okay, because guess what part B is going to be? The same idea. Except this time, it's going to be, instead of the 2, it will be an x. Now, when you plug in numbers, you expect to get out numbers. When you plug in letters, you should expect to get out letters. So when I'm doing f of g of x, I already know what g of x is. They flat out told us what that's equivalent to. So there's no need to really do this, but I'm just showing you that what we did in the first is virtually the same as we're doing in the second. So since I know what g of x is equivalent to, I will take that and plug it in to find what f of g of x is. It's the 3x minus 5. But again, I got to do my order of operations. So it's going to be a little bit more challenging because now I'm not going to have those numbers. I'm going to have letters involved. But I still know I have the 2. 3x minus 5 squared. I'm going to have to write that out and multiply, distribute it out. So when I do my 3x minus 5 by distributing, you should have done this enough to where you know you will get a 9x squared first. That will be a negative 15x. That will be another negative 15x to give me negative 30x's combined. And then a negative times negative, careful, is positive 25. Now that I've done the squaring of that g of x that we rewrote it as, its equivalent form, and we've squared it out, we now have to double everything. And again, that should be pretty easy. Double all of those numbers. You get 18x squared minus 60x plus 50. And then don't forget, we also have to add 1 to that whole thing. And the only thing that we can add 1 to is another like term, and that would be the 50. So our final answer for that one will just be, for part B, 18x squared minus 60x plus 51. So hopefully you guys can do part C. I'll go ahead and give you a couple of minutes to try that on your own. So I'll go ahead and pause the recording, let you guys try that, and then we'll come back and make sure if you don't understand it, we'll go over it. Go ahead and give that a try. All right, hopefully you had enough time to go ahead and give that a shot. G of f of x is the way that we say this. Again, composition, one function composed of another. So I already know that I'm going to have to do g of something. And I know g of something, going over here, is equal to 3 times that thing minus 5. Now, what they're asking me to plug into that, though, is f of x. So going back over here, I know that I'm going to be replacing f of x everywhere there was an x in my g function, because that's what they wanted me to start with, g of something. And that something is now going to be my f of x, which we know is 2x squared plus 1. So again, everywhere you saw an x for your g function, which is what they asked us to do, g of something, then I'm going to replace with the f of x function. Now, we're just going to try to make this look as simple as possible, called simplifying. So I will go ahead and take this and distribute my 3 to only the things that have the parentheses on the outside of. So that will give me 6x squared plus 3. And then it says to take and subtract 5. So my g of f of x, again, plugging in letters, I expect to get something out with that or those letters. Plugging in numbers, expect to get out just a number. I get 6x squared minus 2. Okay, pretty simple. A lot of students struggle with this stuff. They just get a little confused with all the different sets of parentheses. But again, just think about, look at the big picture. It says to do g of something. And I already know g of something is equal to 3 times that thing minus 5. So I set that up. Then I said, all right, well, what do they want me to plug into that g? That was a different function. So I took and replaced everywhere there was an x with what I know f of x is. And then I simplified using my order of operations. Okay, so that's the algebraic way to do it. Let's look at a geometric graph or table. And let's see if you can do similar things using a table. All right, so how would we say that? F of g of 1. And what do we already know? That they're asking us to find f of something. And what is that thing that we need to know? G of 1. Now, here's this table that's saying, all right, with these x's, 1, 2, 3, and 4, if you plug it in to your f function, you will get out a 6, an 8, a 3, a 1. Or if you take your g of x and you plug it into your g function, that 1 will give you a 3. Plugging in a 2 will give you a 5. So here are our inputs, our domain, and here are our outputs, the range for both the f function and the g function. But in this case, we know that we're going to have to do f of something, but before we can find the f of something, we need to use and find the g of something. So we are going to look to our g group in this table, and we're going to look at where x is equal to 1. And we know that g of 1 would yield or produce a 3. So we know g of this x, 1, would produce a 3. So we will replace g of 1 with what we know it's equivalent to, and that's 3. So we replace the g of 1 with the 3, and now it tells us to find f of 3. And what is f of 3? Same thing, make sure you know how to read the table. My x is now a 3, and I want to make sure that I'm in the f function. So when I plug in a 3, I get out. Happens to be a 3. Okay, so again, hopefully that makes sense. It's just a little bit different way, actually an easier way, if you know how to read the table, than doing all of the algebra that we had to do to get this value. We had to plug the 2 into G, work that all out. Then once we had that number, we had to then plug it in for the F and work it all out to find what the F of G of 2 was. So go ahead and give this one a shot real quick. I'll give you about 30 seconds. Should be the most it should take. Go ahead and give that a try, and then we'll make sure that we go over it. All right, hopefully you gave yourself a chance to give that a try. It's the only way that you'll get better at these. G of F of 4. So again, I know I'm going to be doing G of something. And what is that something? Well, I need to find what F of 4 is. That's what's going to go on the inside. So if I could find what F of 4 is, I will then replace that on the inside there with what I know its value is, and then do G of that. So again, go to your F function, go to where it's 4, and that we can see would give us a 1. So we know F of 4 is equal to 1. So that I will replace my F of 4 with what I know it's equivalent to, which now tells me to do G of 1. And that, my friends, also yields a value of 3. Much different way to get there, happen to give us the same value out. All right. So algebraically, graphically, via a table. Well, what about an actual graph? And again, I won't do 2 of this same version, but here is a parabola we're going to call G, and a downwards facing parabola, calling it F. And I want you to find G of F of 2. Go ahead and pause it, see if you can do this one, and then we'll go over it. All right, hopefully that was enough time. How are we going to do this? You're going to do exactly what it says. It says to do G of something. So I know I'm going to end up doing G of something. But in order to figure out what that is, they said to do F of 2. So before I can find what G of something is, I need to find what that something is. I need to go to my F function, and what is this value? They already told us. It could be anything, let's call it X. But in this case, that X, they're saying, is 2. And you should know the X-axis, this is where the 2 is. And am I going to have to go up or down to hit my Y value, my output? Up until I get to what Y value? That would be an output of 5. So I know that I can replace that F of 2, which I know in my F function, when I plug in 2 for X, I get out a Y value. Without having to go and actually figure out what that would be by plugging it in and working it out. They're now showing you either via a table or in this case, via a graph. Okay, so now that I know that, I can go back to what they asked me to find originally, which was G of F of 2, which we know is equivalent to 5. So I'm going to go to my G function now, and I'm going to replace the G of X, like they have here, with the 5. So I'll go to where X is 5, and again, I'm going to have to go up until I hit my Y value, which happens to be a 3. No, my friends, every answer is not 3, okay? Just the examples I chose having to work out that way, okay? So hopefully you've seen all 3 ways. In algebraic, which is what we see the most, the first one we did, and then 2 different graphical types using a table graph and an X and Y axes plotting points graph. Okay, just pay attention to the details. Don't use this one as F and this one as G because this is the first and this is the second graph. Okay, just be careful, should be good. Last thing here, we're going to talk about how to find the domain of a composite function. So remember, composite, one function inside of another. If we want to find the domain of the whole function together, well then that is the set of points for all of those x values first in the innermost one, where those values that we would get out are in the domain of the outer function. Okay, and again, that's a little confusing, so I wanted to break it down for you a little bit more. How are we going to do that? Well, we're going to start by finding the domain of the inside, right? Then we're going to find the domain of the outside function, the f function. And then what we're basically going to do, and I'll highlight it here again for you, is once we found both of those things, the domain of the, try to keep it color coordinated up to top, the domain of the first inner function, the domain of the outer function, then what we're going to do is exclude any of those inputs from the domain of the inner function where the outputs are not in the domain of that outer function. Okay, that then would be the domain of the composition f of g. Now, by the way, what if it was g of x that they wanted us to find the domain of? Just flip-flop the order. Okay? Don't worry too much about that, but that is something that we should be able to do. So the last thing I wanted to cover with you all before we get to the next section is what we call a decomposition of a composite function. To decompose means to break down. So what we want to do is take some nasty old function like this and try to break it into smaller parts. This is something that's going to be really, really important for you guys in second semester calculus. Being able to break them into simpler, still representing the whole thing, but breaking them into smaller, simpler parts so that we can do this thing called integrating. Okay, so for us, they're giving us this big old f function, nasty fraction with the square root in the denominator, and what we want to do is break it down into 2 different functions. So let's call it the next 2 letters, g of x and h of x. And if we were to rewrite this function as g of h of x, again, I'd rather you not write it like this. Okay, try not to use that weird little o, which is short for of. G of h of x. It's easier to say it and see it as g of h of x. What would be the inner function? And what I think is easier is to find the outer function first. Look at the big picture. What do you see? Probably a fraction. So I know that g function that I'm going to rewrite. I'll use different colors. My g function is going to be the big picture, the outside. And it's going to be 4 over 3 minus, well, that's where it gets a little ugly, doesn't it? So my g function, I'm just going to call this something. Usually we use the letter x to represent unknowns, but I don't like that big old mess. So I'm trying to simplify it. Here's a simple way to write the big version of this. 4 over 3 minus something. And that something we're just going to call x. But if I wanted to have my original function, f of x, back, then what would I do with this? Well, I would have to have something different, h of x, that I'm going to plug in to the g of x to represent and get back my original big nasty f of x, they're calling it. So we rewrote it in simpler form as 4 over 3 minus something. 4 over 3 minus something. So what can we call that h of x that we could replace those with so that we have g of h of x, which is equivalent to the original function we're calling f of x. Well, as you can see, we're just replacing the nastiness with that, which means h of x would be the square root of 4 plus x squared. Now, there's a couple different ways to do this. You could have left this as the square root of x and then just called this part your h of x without the square root. That would also work fine. Okay, so there's a couple different answers to this, but I wanted to show you what I felt like was the simplest, outer, bigger version of this. And the ugliest part, we will call the inner. And if we were to replace that here, everywhere we saw an x, then that would be our g of h of x, which we're calling our original f of x. Okay, so hopefully that made sense, because that is the composition of a function in several different ways, algebraically, in a chart or table, and also graphically with an x and y axis. We talked about the domain of it a little bit and how to break them down and look at them as different parts as well. All right. So now we'll go ahead and pause and start working on this for a little bit together in our groups. And then we'll come back and do the second section for today. All right. Well, welcome back to the next section, 3.5 in our book, Transformations of Functions. And as you can see, I put on here that this is a very important section for your entire mathematical future. All right. Not just this class in the immediate future, but also when you get to calc. Okay. The more of these you know off the top of your head and you can just visualize, the better it is. Okay. So as you can see here, before we start transforming these things, notice it didn't specify, it just said functions in general. We got to make sure that we can graph what are called their parent functions. Okay, this book often calls them the toolkit or basic functions. Okay, so I'm going to go ahead and pause it real quick and I will minimize and go one at a time. Try to graph as many of these as you can in about 3 minutes. Okay, so I'm going to go ahead and minimize this so that you can see there's quite a few of them that we're going to be talking about. And the more of these you know off the top of your head, the better it is. So go ahead and pause it here, see how many of these that you can do. And remember, if you ever are unsure about what a graph looks like, plot points. Draw a little, what we call T-chart. For lack of a better term, it looks like a T. Inputs, outputs. And usually we like to input a few positive and a few negative values so that we see what we get out. And each one of those X's and Y's represents a point. All right, go ahead and pause it. Take a few minutes, 3 to 5, hopefully. See how much of this you know. If not, we will quickly review it. Ready, go. All right, let's see how you did. Now, again, some of these you should definitely know off the top of your head. Others, it might have been a while, or you may not have even seen them before. Only one that I think that you may not have seen is this one. Maybe that one you should have seen. Okay, but these 9 are some of the basics. They call them toolkit functions in our book, but these are the basic ones that hopefully you recognize and or can visualize immediately. So this is called the identity because they're saying that x is equal to y. So no matter what you plug in for x, you will get out the same thing for y. So 0, 0, 1, 1, 2, 2, negative 1, negative 1, and so on and so forth. So this is just the basic line y equals x. Okay, pretty simple there. Now, when we start squaring things, square rooting, cubing, absolute values, raising it to the power, or even doing the reciprocal, much changes, right? Now, again, if you were to plug in some x values, you'd have to square it to see what you get out. Again, input, output, right? So for this one, I know if I take 0 and square it, I get 0. If I take 1 and square it, I get 1. If I take 2 and square it, though, I get all the way up to 4. So you can see a straight line is not going to hit all of my points, especially not everything in between that we're not going to plug in because it's more difficult. Negative 1, square that, you also get 1. Negative 2, square that, you also get 4. So you can see that this has a mirror image on both sides. We call that being symmetrical. Okay, so we get this rounded U shape called a parabola. And that is for anything that has a square. Now, can it be more wide? Can it be more narrow? Can it be shifted around? Absolutely. Those are what we call the transformations that we will do by adding, subtracting, multiplying, dividing things to this. Same thing with the line y equals x. We know it can be more flat as far as our slope goes. We know we can have steep negative slope. We know it also doesn't have to go through the origin. So again, those are the transformations in our preferred form of a line is slope intercept form. Okay, so again, all kinds of things that you should know. How about the square root of x? Anybody remember that one? Well, again, if you don't, plug in things you do know the square root of. I know the square root of 0 is 0. So that will be my origin, is where we're going to start again. Okay. Then when I take the square root of 1, I know it's 1. But I'm going to go all the way to 4 to get my next square root, which would be just up 2. So again, I could go all the way out to 9 if I wanted to. It'd only be a 3 output. Now, I'm not going to have the other side of this because all of these are negative values. And all negative values under a square root are imaginary. And we are dealing with the real x and y plane. So in this case, you only get this half of a parabola on its side. We don't get negative y values because we know when we take the square root, we only get out positives. We can't take negative values because we get those imaginary numbers. Okay, those should have been pretty easy. That's why I started with those 3. Cubic, also one that you should know. Again, if you don't, just plug in things that you do. 0 cubed, 0. 1 cubed, 1. 2 cubed, all the way up to 8. Negative 1 cubed, careful, is a negative 1. Negative 2, all the way on down here to negative 8. And you can see that these get very large very fast, because if I went all the way to 3, I would have had to cube 3, which takes me all the way to 27 for my value. So this jumps very quickly in both directions. Don't forget your arrows. As we talked about with domain and range, those matter. Okay, we can talk about the domain and range of each of these, but let's just talk about graphing them first. How about the absolute value? Are there any restrictions on what we do there? Absolutely not. Plug in anything for x, take the absolute value, which means the distance from 0, and you will get it. When you plug in 0, the distance from 0 is 0. So that's our output. Plug in 1 or -1, you are a distance of 1. Plug in 2 or -2, you are a distance of 2. So we actually get these positive slope and negative slope lines that make this V shape for the absolute value. Okay? Again, we will take these things and we will make them more narrow, more wide. We'll shift them around. We'll flip them upside down. All kinds of transformations we will do to all of these. But if you know these basic formations of these graphs, then all the little tweaks that we talk about should and hopefully be easier to do if you know how to graph all these. Now, I'll go ahead and get to what are called exponential functions because our x is up in the exponent, and these logarithmic. Now, I'm talking about basic ones here where we have a base of a particular number called e. Yes, it is a number. And then the natural log. So it's still a logarithm, which is why we write L in. That is not an I. Okay, that is a lowercase l. But the natural log gives us a base of e as well. And if you remember, e is like pi, but pi is spelled without the e. Okay, pi is an irrational number. E is an irrational number. Right? So each of these individually have their own mark because they are dealt with in different formats very frequently. Okay, E with compounding interest and the growth and decay, pi with circles and their circumference or perimeter and area. Okay, so E is a little bit less than 3, pi is a little bit more than 3. All right, so when we're dealing with these things, we're going to be talking about, well, what would happen when I have a little bit less than 3 to the 0 power? What is anything to the 0 power? Hopefully you remember that is a 1. So when I plug in 0, I get a 1 out. What happens when I plug in 1? Well, what is 3 to the first? It's 3. But remember, they took one of the e's off of 3, so it's a little less than 3. Okay? So when we go to mark this, I don't really care that it's exact. I just want you to know the basic formation of this graph. And again, what would happen if we plugged in a 2? Well, we'd have about 3 squared, which is about 9, so 8 point something. Okay? So again, way up there at just below 9. Now, careful. What happens when we plug in something like a -1 or a -2? What happens when we take a number and raise it to a negative exponent? Well, hopefully you remember it takes this and moves it across the division bar, aka reciprocal. It flips it down and it'll give us that 1 over e, which is about 1/3. So a little less than 1 here. And what if I had it squared then? Well, then we'll have that 1/9 or 1 over 8-ish, right? So it just keeps getting smaller and smaller and smaller. But if I wanted to continue this on, I know it's going to get bigger and bigger and bigger. If I want to continue this on, do I keep getting smaller and smaller and smaller? Will it actually get to be negative values? No. This will become e to the 3rd, e to the 4th, e to the 5th in the denominator of it, which is still always going to be positive. So it will get smaller and smaller and smaller and smaller. So small, in fact, that, you know what? I'm going to draw a borderline. And that borderline is what we call an asymptote. Just to let you know that, hey, this is going to keep getting smaller and smaller and smaller, but it's not going to ever touch or cross that x-axis. Okay, so I will draw this out real quick for you, along with this, what is called horizontal asymptote. which is an equation of a line, where what is true about everything? Y is equal to 0 everywhere. The x's can be whatever horizontally, but it's neither up or down in this case. But of course, we can shift it up and down. Okay? So we are dealing with all different shapes of graphs. This line, this U-shaped parabola, this half of a parabola on its side, this elongated S for cubic, this V for absolute value, and now this J-shaped curve called an exponential, an increasing exponential. Well, what about its inverse? The reverse form is called a logarithm. And if it's reversed, then that means the asymptote that runs along the x-axis will now run along the y-axis. That 0.01 will now become 0.10, as will all of these other points. So from left to right, we notice it was increasing. Well, then from left to right, we know that this is going to increase as well. And the cool thing is, this graph, if I graph them on the same thing, will be symmetrical about the line y equals x, because these are always the same, no matter if I switch the x and the y, like we talked about doing the inverse of with these two things. Okay, so I will quickly graph that one that goes along with it in a different color here. And that would be where we have a vertical asymptote now, where x is equal to 0 everywhere, the 0.10, and all of the other values that go along with it, like we talked about, flip-flopping all the x's and the y's, doing the reverse or inverse. Okay, lastly, what about these reciprocal functions? When we take y equals x and we do the reciprocal, flip it. Now we have issues because we're dealing with the fraction. There was no issues for x's or y's on this. The domain is everything, negative to positive infinity. The range is everything, negative to positive infinity. Because no matter what I plug in, I will always get out, and I will also get out every y value. But when we deal with fractions, we have to be careful with the denominator. We know that these cannot have denominators that equal 0. So if I was to say that x cannot be 0, what if I tried to plug in 0? What would it happen if I asked you to find f of 0? Well, you get 1 over 0. And if you have something like 1 and you try to divide it 0 ways, it's impossible. You can't do it. Therefore, we say it's undefined. But what does that mean graphically? What are we going to draw graphically to let you know it's undefined? We're going to draw a little thing called an asymptote. And an asymptote is a borderline. It's something that I know that this graph will approach and get really, really close to, like we said, this one would here and this one would here. So to the right of it, which since it's at 0, that means these are all positive values. What would happen if I plugged in a positive number for x? What would I get out from my y values? Would they be positive values or would they be negative values? Because they're positive in there and I'm taking 1 and dividing it by it, we know we would get positive values. So the graph of this thing is going to be approaching positive infinity. And then when I plug in 1, I would get a 1. I plug in a 2, I would get a half and a third and a fourth. And notice what's happening again. The bigger the x, the smaller the output, the y value. And so what would happen is we would again approach that 0. We would never actually reach it. So it flattens out. You guys have heard a lot about that the last couple of years with a little thing. I don't know if you've heard of it, COVID, right? That's something that we talked about, flattening the curve, because these were growing exponentially with people contracting it. So we were trying to flatten that curve and smooth it out instead of it continuing to grow exponentially and people dying or getting really sick from it. Okay? But what about the left side? What about all of these negative values to the left of 0? What would happen if we plugged a negative value in for x? Well, when we take 1 and divide it by a negative number, we know it's going to stay negative, which means this one is going to be approaching this direction, negative infinity. And of course, a -1 would give me a -1, a -2 would be -1/2, 1/3, and so on. So this one would do that and also have this horizontal asymptote. Well then, my friends, what would happen if we squared it? What would still give us an issue in the denominator? Zero. Even though it's squared, if we plugged in a 0 and squared it, we'd still get 0, and we know that cannot be. And it's the only thing that wouldn't. But what would happen when I plugged in a 1? Well, I get a 1. What about a 1/2? If we have 1 over 1/2 and it's squared, it would become 1/4. And we know that we don't like dividing by fractions. We have to multiply by its reciprocal. So that 1 divided by 1/4 is now going to become a 4. And what if I plugged in, instead of 1/2, 1/3 or 1/30th? All of these really, really small numbers here are going to get really, really big really fast. So again, we will get positive values, and they will also again approach 0. But what's going to happen when I plug in these negative values? What if it's negative 1/2 or 1/3 or 1/25th? What happens when we square negatives? It's also going to yield a positive. So you will take this one down here and flip it up to be positive values. And that, my friends, is the difference between 1 over x having 1 positive and 1 negative versus when it's squared and then both being positive output values. Okay? If you haven't seen any of those before, now you have, and you need to know them. Because what are we going to do now that we know all of these basic toolkit, they call them? You got to have these on your tool belt so that you can then take them and transform, manipulate, move them around, flip them, do all kinds of fun things. Hopefully you guys brought your yoga mat, because we're going to talk about stretching, reflecting, all of that fun stuff together we called a transformation. Okay? So here they are again with a little bit cleaner version and also listing their domain and range. So if you guys want to talk about any of the domains and ranges, this would be the time to do it. And remember, domain, we're talking about the x values, the inputs, and starting from the left and going to the right. What values can we plug in that we get something out? Well, anything to the farthest left and right. So the domain is negative to positive infinity. Again, notice parentheses around those because we cannot include them. Infinity is an idea. It's not something that we can put our finger on or plot a point of. The range, same thing. We're going to go smallest to biggest, but this time in the y's. And since this arrow goes down and up forever, and we hit everything in between, again, negative to positive infinity. Left to right for smallest to biggest in the domain, bottom to top for our range, our y values. Domain for this, it will go out in both directions forever. So technically, I will hit all x values. But my range, I will not hit any of these until I get to 0. And then because it goes up, I will hit all those other values. So that's why we include 0. It is a value that we get on our y and everything above it. Okay, square root function from here over for my domain, and from here slowly, but eventually I'll hit everything in the y values as well. There's our cubic. I even included the cube root if you wanted to see it, and that reciprocal function. Domain goes down and up and out forever. So since it's going to eventually hit everything to the left and everything to the right, we include everything. Definitely easy to see. There's no limit in the y values. It goes down and up forever, everything. This one, notice it's just reversed. All of our inputs and outputs. Okay, but that means, again, domain and range, everything to the left and the right. And even though it slowly goes down and slowly goes up forever, because it goes forever, negative to positive infinity. Now this one's a little weird for my domain and range. As you can see, we got that union, that weird looking U without the little leg on it, to unite certain things. You can see that this is going to go left forever. Sorry. This is going to go left forever. Okay, we'll try that again. This is going to go left forever, and this is going to go to the right forever. But do we hit everything for our x's in between? Just about. There we said was one thing that would not work, and that was a 0 in the denominator. So we have to exclude the 0, but unite everything to the left and everything to the right of it. That includes my y values as well, that skip the zeros. So you guys get the idea for domain and range. Somebody asked about that a little bit earlier. Again, hopefully this clears it up. And even though it looks like it hits this, remember, there's a dashed line here called an asymptote. Weird spelling, I know. Silent P in there. The asymptote is that borderline to let you know, man, it's going to get really, really close to 0 for my y values, but it will actually never reach that 0. Same thing here for the logarithm, the natural log. All right. So hopefully you guys know most, if not all of those, including the absolute value that was on here. All those graphs that we talked about, that we drew. I had you guys try and draw as many of those as you could, and then talked about the domain and range of each as well, and also gave you the names of each. Okay? Because the main thing that we're going to then do with this is try to generalize it in what those basic functions can then look like when we manipulate them. Okay? So again, I highlighted some of the main things. Now that we quote unquote know how to graph all these, some you already know, others you're also going to have to memorize. What's going to happen when we change them around, manipulate them? What is that going to then do to these things? Right? So remember, knowing those parent or toolkit functions is important. Make sure that you take the time to memorize them. It's going to help you. It'll pay dividends in the calculus series. We want to be able to look and graph them quickly. And once we do, then when they throw little tweaks here and there, that cause us to shift either vertically or horizontally, stretch, compress, or even reflect. You'll know what that also does, and then can answer questions about it quickly. Okay. So again, if you can see these things in your head and very quickly, it's going to use very little technology or other things when asked questions about them. You'll be able to visualize and start doing the other things in calculus. Now, don't forget, we're going to add things on, some of the things we talked about last time. Domain and range, which we just reviewed again, where it's increasing or decreasing. That'll be something very important to you in calculus, as well as these local and absolute max and mins. Those will be other things that you will use calculus to be able to find very quickly. All right. So to wrap this all up, if I was to give you any one of those functions, you would have to know what the A, B, H, and K would have the effect on that function for the X and the Y's. Again, what's going to be up here could be squared, could be cubed, could be a square root function, could be a logarithm, right? All those absolute value, all of that is going to change. But what's not going to change is the effect that these things will have on it. And if it's inside of these, whether they're brackets or parentheses, with the X, then you should know if it's inside with the X, it's going to affect the X axis somehow. And if it's not in with the X, it's on the outside, then it's going to have an effect on the Y. All right, and here's my little helpful tool for you guys to hopefully remember. How these things will affect the X's and the Y's. X's are X's because they wanted the opposite of us. Well, the same holds true. If it's being multiplied by some number, you're going to end up dividing by that number. If it's being subtracted, you're going to end up adding and shifting all of the X values by that. Right? Where Y's, and maybe I should write this a little bit better so that you remember. Y's are Y's. We do what they say. Because they're Y's. Okay? Or if you want to make it a little bit more relatable, if you're a male, wives. Okay? So X's want the opposite of us, which is why we will do the opposite of these things. Where Y's are Y's, and we will do exactly what they say. So if this is multiplied by a 2 on the outside, I will multiply all my Y values by 2, which will stretch my graph, whether it's a parabola, an absolute value, square root, all those functions. Where if it's plus or minus some value out here we're calling K, then we will do exactly what it says, and we will shift all of our graph, our entire parabola, we'll shift it up 3. down 5, whatever it might be. And I will use one other term here loosely, and I will call it the starting place or the vertex of each one of these is equal to h comma k, because that will be how we shift the entire basic graph. Now again, why is it positive h and positive k? Because whatever the sign is with that x, you will do the opposite. So that's why they put a negative there. Because if I ask you for the opposite of 5, you would say negative 5. So again, this is the symbol that we use for opposite. Okay. So of course, that's going to take some practice. And I wanted to also quickly mention how these can be used in these special cases in calculus where we talk about even, odd, or neither. When we look at functions and how they are graphed, some of these functions you can tell are symmetrical about the y-axis. And some are symmetrical about the origin. Either way, you will be able to see that quickly. And if you know, because it's even or odd, it's called, then you can use that to find things in calculus a little bit more quickly. Again, special cases in calc. Okay, so it is even function. It's symmetrical about the y-axis. If it's an odd function, then it will be symmetrical about the origin. And how we test that is very simple. All you do is you go to your function, whatever it is, and you plug in a negative x, the opposite of what you had your function as. And if it comes out the exact same thing as your original function, then it's even. If you plug in and it comes out the opposite, when you plug in that negative x, you get the opposite of your original function. Everything is the exact opposite sign. Then opposite means odd. Even means the score is the same. So let's take a quick look at some of these graphs here, and hopefully you can tell me which ones are even and which ones are odd. Now, obviously, you should be able to look at the exponents, the degree of this, and also tell me y equals x to the first. What do you think, even or odd? Well, if the degree is 1, that's an odd number. This is going to be odd. What about x squared? I know that's an even number. So then even. Now let's stop there just for a second and look at the graphs. We said if it's even, it's going to be symmetrical about the y-axis. Because no matter what I plug into the right or the left, a positive or a negative, I will get the same y value out. That's what we mean by even, same. But for odd, if I plugged in a 2, I got a 2. But when I plug in the opposite, a negative 2, I also got the opposite, a negative 2. So notice the point 2, 2, I got the exact opposite, which was a negative 2, negative 2. So that's what we mean symmetrical about the origin. Whatever you get here, you'd get the opposite here. It's symmetrical about this. So let's look at another obvious one, like a cubic. What do you think? Definitely not even. Is it odd just because it's x cubed? Looks like that is the case for most of these. But if you start adding in x squareds and x's and other numbers, it gets a little bit more involved. That's when we can use this form to see whether it is symmetrical about the y-axis or the origin. Okay, so very quickly you can see that, again, 0, 0, that is that vertex, that starting point for every one of these. But when we pick that up and shift it up, down, left, right, whatever, start stretching, right, or reflecting it about the x or y axis, that's when things start getting a little bit more tricky, competitive for us to stay on task. But if you again notice, I don't know why it keeps doing that, sorry. If I plug in 1, I would get out a 1, because I know when I cube 1, I get 1. Here, -1, -1. So again, hopefully you see that it is symmetrical about the origin. Okay, so without doing a ton of examples, I wanted to at least show you the basics here, set you up to show you what things would affect what. And again, we know if it's being done to the x, it's going to affect the x, and in the opposite way. If it's not being done to the x, then that means it's going to affect the y value. And we know y's will do exactly what they say. If it says to multiply by some fraction or some number, we know that that's going to multiply our y's if it's bigger. If it's a fraction, it's going to shrink it down. Adding or subtracting, shifting it up or down the entire graph by that y value. Same thing for our x's, but remember, opposite effect. If it's a 1/2 here, then we're going to end up multiplying by 2 and making all of our x's twice as big. All right. So now it's time to put the talk aside and start working on this stuff and seeing if you can do them. That's where the group quiz comes in and your homework. All right. That's all I got for you. Until next time, I'll see you guys. Good luck.